ladies and gentlemen, this is going to be the video where I explain our third primary topic of equilibrium, how to determine concentration when given an equilibrium constant, calculating concentration from K. Again, this is going to be split into two videos, one where I sort of talk about the basic idea behind it and I go through one example. The second video will be me using the concept of calculating concentration given K when applied specifically to a Ka problem and a KSP problem. So I'm starting with this slide again because these three steps are really your crucial set of three steps for solving essentially any equilibrium problem. You want to start by writing a reaction if one hasn't been given to you so that you can describe your system. Then from the reaction, you want to fill in an ice chart as best as you possibly can. After you filled in the ice chart, then you write the K expression and you plug in and you solve for whatever it is that you're missing. Now, when we were determining K from concentration, we were able to fill in the ice chart completely. Now we've got the opposite situation. We do have the value for K, but we're missing information about concentration, which means that when we have that ice chart, things are going to look a little bit different. We are lacking information about concentration. That's what we're trying to find. We are trying to determine concentration, which means that we will have unknowns, x's, in our ice chart. We're going to have unknowns, x's, in our equilibrium expressions, but because we know the value for K, the equilibrium constant, we can set up the expression and then solve for the unknown concentration, given the fact that we know the value for K. And this is going to be used in Ka, Kb problems because H plus or OH minus, those are concentrations that you could solve for from your equilibrium expression if you know the Ka or Kb value, and then use that to determine either pH or pOH depending on what the question was asking, what it was looking for. So in using unknowns in our ice chart, we have to sort of go through a process. Sample problem. Given 0.1 molar COCl2, determine the equilibrium concentrations of carbon monoxide and chlorine gas, given that the Kc value for this reaction is 2.19 times 10 to the minus 10th. So the reaction is provided to us. I really want to stress that we're following the same fundamental three set of steps. We write a reaction, we fill in an ice chart, and then we go to the equilibrium expression. We plug in and we solve for whatever it is that we're lacking. The distinction now is that we know K and we're looking for concentration. So we're going to do exactly that. Now the reaction is already written, which is great, so we're just going to go straight to the ice chart and we're going to start filling stuff in. Now, scanning the problem, we're only given one concentration right there, and it's 0.1 molar COCl2. And when we're given information about reactants, really that's our initial concentration, 0.1 molar COCl2. Recall, though, that if you're not given specific information about the products, that means that we're assuming that we are starting at 0 molar, that we don't have any products when we begin. Nothing in this problem says that we are starting with 0.1 molar carbon monoxide in addition to the 0.1 molar COCl2, which means that we are very confident in saying that we are starting at 0 for the products. But like I said, we have to be able to fill in our ice chart. That's the whole point. We need to fill in the ice chart. And looking back up at the question, no other concentrations are given to us. We do not have any equilibrium concentrations. So this is where we're going to use X. Because we cannot fill in any more numbers into the ice chart, we do not know what the change is, which means that we're going to say that the change for the COCl2 is minus X. We don't know what it is. We cannot put in any additional numbers. So we're going to basically make that statement that we don't know what it is, but we're going to call that change X. Then, remember that the change is tightly linked to the stoichiometry of the problem. We're going to use the fact that the COCl2 has a coefficient of 1, the carbon monoxide also has a coefficient of 1, and the chlorine gas also has a coefficient of 1. These are in a 1 to 1 to 1 relationship, which means that if the COCl2 goes down by X, because it's a reactant, so it's being used up. Then the carbon monoxide, it's a product. It will go up by X. It's a 1-to-1. You lose X amount of the reactant. If they're in a 1-to-1, you will gain X amount, the same amount of the product. Now the chlorine gas is also 1-to-1, so this will also be plus X. You lose reactants, you gain products, and this allows us to complete our ICE chart by basically saying, look, we don't know what the change is, but we're going to figure it out. Because then we can simply say that the equilibrium concentration of the COCl2 is 0.1 minus X, that the carbon monoxide equilibrium concentration is X, and the chlorine equilibrium concentration is X. You have now filled in your ICE chart. Is it filled in with numbers? No, but that's okay, because we want to determine, as the question says, the equilibrium concentrations of CO and Cl2. And when you look at what you've written, look, the equilibrium concentrations of CO and Cl2, well, that's X. They are X. So if we can figure out what X is, we have answered the problem. We have finished the problem. So if you do not have enough information to fill in your ICE chart with numbers, then you start filling it in with unknowns. Minus X plus X plus X. They're all the same because they're in the COCl2, the CO, and the Cl2 are in a 1-to-1-to-1 relationship. So if you lose 1 mole of the COCl2, you gain 1 mole of the CO, and you gain 1 mole of the Cl2. That's the second step of our 3-step process complete for equilibrium problems. The third step is to go to the equilibrium expression. This is the same fundamental process as we did before. So we're going to write the Kc expression. I'm just going to write it out completely. We've got carbon monoxide raised to the first times the chlorine raised to the first, products of our reactants raised to their coefficients, over the COCl2 raised to the first. Now, where instead before you were looking for the value of Kc, we know the value of Kc. So now we're going to plug in what we know. 2.19 times 10 to the minus 10th is equal to, well, equilibrium. We're always looking at our equilibrium line from our ICE chart. X times X over 0.1 minus X. That right there is totally solvable. You totally know how to do that in your math classes. I know that you do. So at this point, it really just becomes a question of algebra. However, if you're looking at that, hopefully you're starting to realize that that's going to get a teensy bit gross when you solve it. You're going to have to carry the 0.1 minus X over to the 2.19 times 10 to the minus second side, and then you're starting to look at a quadratic. You will have a quadratic equation, and you'll have to solve the quadratic equation. Now, I know that you know how to do this. I know that you know the formula for the quadratic equation, and you're capable of using it to solve for the values of X. But I also know that that's very obnoxious. It's very obnoxious. And realistically, chemists are lazy. They are. They're lazy, and they want to make their lives as easy as possible. So I've got a lifesaver for you. Rather than having to solve the quadratic equation, you are going to make an assumption. Oh, and it's going to make your life so much easier. You're going to make an assumption. My college professor, I actually found this in my notes from when I took college in chemistry, when I took chemistry, introductory chemistry in college, which, by the way, is virtually identical to this course. He called it the golden approximation, and this is the assumption. This is crucial because I have to talk about this a little bit. This is not something you can make all the time. If your K value is significantly less than 1, which 2.19 times 10 to the minus 10th, yeah, I'd say that's significantly less than 1. If your K value is significantly less than 1, that is saying that the amount of product you have in comparison with the amount of reactant you have is very, 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 very small, right? Products over reactants. But if we get a value that's way less than 1, then we know the numerator is virtually tiny in comparison with the denominator. Products are much less than reactants. We can assume that X is negligible in comparison with the amount of starting material that we had. That is to say, 0.1 minus X is approximately 0.1. This is the assumption right there. 0.1 minus X is approximately 0.1. Basically, this idea is sort of saying, if you take Bill Gates' salary and you take Mrs. Julian's salary and you subtract Mrs. Julian's salary from Bill Gates' salary, you subtract a relatively small number from a ridiculously large number, you still get essentially Bill Gates' salary. Let's say, for example, you take $400 million and then you subtract $10,000 from $400 million. Guess what? You still have about $400 million. And you can assume that it's approximately the same in terms of any measurable difference, any really effective difference. That's kind of the idea behind it. We are assuming that x is so small in comparison with 0.1 that you subtract x from 0.1 and you're not going to see a difference until you're like 8 decimal places out. Now, this assumption is going to make your life much easier. But as a trade-off for that, there are two things that you have to do. The first thing that you have to do, that you absolutely must do, is right here. You must indicate that you are making an assumption. Meaning, you have to show me somewhere on your work that you are assuming that 0.1 minus x is approximately 0.1. And by the way, this thing right here, that approximation, and this statement, 0.1 minus x, squiggle, squiggle, 0.1, that's all I need to see. It is understood that that is how you are stating your assumption, but that must be present. So you basically can't set up your ICE chart, have 0.1 as the initial, minus x as the change, and then 0.1 as the equilibrium concentration. You can't do that. You do have to show me that you know that it's 0.1 minus x, but then that you're assuming that 0.1 minus x is approximately 0.1. Furthermore, you then have to check your percent ionization afterwards. So you have to do two things if you want to avoid the quadratic equation. You indicate you're making an assumption, you check percent ionization afterwards. The rule is that if the compound is less than 5% ionized, if your percent ionization comes in at under 5%, then your assumption was okay, meaning the percent that came off was relatively small in comparison with the amount that you started with. Your assumption is valid and it's not significantly affecting your results. If your percent ionization is greater than 5%, that means that you have no other choice but to go back and solve for x via the quadratic equation. So I'm going to finish the problem from before, and we're going to actually calculate the percent ionization and see if our assumption is okay. So we're going to go back to that COCl2 goes to CO plus Cl2, and if we make our assumption, remember our equilibrium expression had been the k value equals x squared, right, x times x over 0.1 minus x, but we said, oh, well, 0.1 minus x is approximately 0.1. And that's going to make your equilibrium expression a lot prettier to solve for, a lot easier to solve for. This really becomes greatly simplified, and it'll save you some time. So then this is, okay, you just cross multiply the 0.1 times the 2.19 times 10 to the minus 10th is equal to x squared. Simply take the square root of that value, and you get an x value of 4.68 times 10 to the minus 6th. So that's the math. We have now solved for x. Recall that from our ICE chart, x is equal to the equilibrium concentration of the carbon monoxide, and it's also equal to the equilibrium concentration of the chlorine gas, right? Because that's how we had our ICE chart filled in. That's what x represented. X was the equilibrium concentrations of these guys, which means, hey, we just solved for x, and the question is asking for the equilibrium concentrations of these two things. We can answer that question now. X is 4.68 times 10 to the minus 6. X is also these concentrations. Great. What are the concentrations of CO and Cl2? 4.68 times 10 to the minus 6 molar. But you made that assumption. You got to make sure that that assumption was okay. You have to do your check. Percent ionization is part over whole. We are assuming that the part that came off, which is our x, is small in comparison to the whole that we started with, the 0.1. Right, so we're looking for percent ionization, part over whole. Now, I'm calling it percent ionization. Technically speaking, in this reaction, it's not being ionized. It's simply a reaction, essentially how much of this reacted, how much of the COCl2 turned into CO and Cl2, but it's still the part. So it's always going to be set up as X over whatever your initial concentration was of your reactants. Now, in this problem, the initial concentration of our reactants was 0.1. Basically, it's the idea of saying it's part over whole. So to go back to the Bill Gates, Mrs. Julian's salary thing, if you assume that you subtract Mrs. Julian's salary from Bill Gates' salary and you still effectively get Bill Gates' salary, Mrs. Julian's salary is the part, Bill Gates' salary is the whole. That's what we're looking for. We're taking away Mrs. Julian's from Bill Gates'. So it's always that part over whole. So X over 0.1 and then times 100, because this is percent, well, we have the X value that we solved for right there. So this is 4.68 times 10 to the minus 6 divided by 0.1 times 100. When we do this math, if this winds up being less than 5%, then we do know that X is truly negligible when compared with the amount that we started, and that assumption is acceptable. And hopefully by looking at this, even if you're not doing the math, you're realizing that, yeah, there's no way this is going to come out to be anywhere near 5%. This winds up being 0.0047% reacted, essentially, which is way less than the 5 that we need. Now, when you're in terms of showing work for this, for the check, realistically, it's this bit that would sort of be needed. And even if you simply said that this, if you sort of do this math, and you said instead of like equaling the 0.0047, simply said that it's less than 5%, that would be acceptable in terms of showing work that for that check. But so that's the trade-off if you're making this assumption, which really does make your life easy because you're avoiding using the quadratic equation. And on the multiple choice on the AP Chemistry exam, you will be asked to do this type of problem without a calculator, and there's no way to do this without a calculator without making that assumption. Now, of course, it's multiple choice, so they're not looking for your work, they're just looking for the correct answer, but you will sort of be expected to understand that 0.1 minus x is approximately 0.1, which makes solving the problem without a calculator much simpler. So that's the idea behind calculating concentration from K. We have to use X in our ice chart, and we have to make this assumption. And then my second video is going to be going through this process with a KA problem and a KSP problem.